France is known perhaps mostly for its cooking. And as a French child, I had the great privilege to be exposed to some of the best foods in the world. What's interesting about that aspect of cooking is that it's a mix of art and science. So as a scientist, I appreciate the science of making food, the ingredients, the protocol, the process, and you have to follow the recipe to some extent. But I also really love and enjoy the art parts of cooking, where you don't have to follow the protocol, you don't have to exactly measure. And one of my favorite things in the French cookbook is French crepes. Start with a little bit of flour, ideally a high-grade flour, but any flour will do. And depending on how sweet or salty you are that particular day, you can add a little bit of sugar and or add a little bit of salt, whether you want sweet or savory crepes. And one of the great things about French crepes is you can have it both ways. You have this chemistry and alchemy at the same time of putting those ingredients together and then let them evolve, let them change shape. And you can add a new ingredient, you can change the recipe, you can change the formula, you can change the equation, and then usually more interesting things happen when you have a more diverse set of ingredients. But what if the egg is a little bit different? What if the flour is a bit of a different batch? If the ad hoc, unpredictable part of the process is what makes it more exciting, and it's also more playful. It's more fun to not have to follow the exact same recipe every single time you make the dish. And as they say in French, voila. I had always had an inclination or proclivity to be more adventurous, you know, as a child, from what you eat to how you play to, you know, who you hang out with and to what you do, right? You want novelty, you want excitement, you want things you've never done before or seen before. You have to have new adventures all the time. But if you're curious and you want to explore the unknown, you have to go places nobody's ever been before. You have to think of ideas nobody has had before. You have to think of means to solve some problems that nobody had thought of before. As a trained organic chemist, as a trained engineer, as a trained geneticist, as a trained microbiologist, as a trained food scientist, as a trained businessman who went to business school, I have a lot of ingredients to work with. As an innovator, I want to use all those different tools, all those different learnings from different schools and different disciplines and different classes to find a way to help me navigate and then get to places that I don't even know exist today. One of my first jobs at Danisco in the spring of 2005 was to study dairy starter cultures. And my job was to understand what genetic content was in those starter cultures that gave them beneficial attributes. And one of the ways that we did that at the time, you know, like circa early 2005, was to just sequence their genomes and annotate their genomes and analyze their genomes. And one of the biggest problems that we have in the dairy industry, unbeknownst to most people, is that in very large fermentation vats that can have hundreds of thousands of liters of milk to turn into yogurt and cheese, occasionally, and unfortunately, there are viruses called bacteriophages that come from milk that's not sterile and occasionally attack those bacteria. So one of the specific questions I was looking into was, how do bacteria become resistant or sensitive to certain phages? And what we were doing was using genetics to sequence the genomes of the bacteria and doing genetics to sequence the genomes of the phages to understand who they are, where they come from, how they evolve over space and time, and how they interact with each other. And oftentimes, when you try to assemble a chromosome, the assemblies break down at locations that are repeated more than one time in the genome. So repeated elements are difficult to assemble, and one of the repeated elements that I was working on at the time to assemble by hand is called spaced interspersed direct repeats, SPIDER, also now known as CRISPR, clustered regularly interspaced short palindromic repeats. And at the same time, pretty much the same day in the same space, I'm sequencing the genome of the phages that are problematic in my starter culture. And I realized that some of the spatial sequence I'm assembling are perfect matches to the viral sequences that I'm also assembling. And my first thing is I contaminated the two. But as you look into it, you realize it's not a mistake. It looks like a mistake, but it's not a mistake. So realizing it's not a mistake is part of the discovery process. And then realizing that what it looks like actually is there's pieces of the phage genome that are actually in my bacterial genome. It's one of those eureka moments you have in your life, maybe one time, and you realize, oh my God, there's a correlation between the presence of a piece of the phage DNA in this region of the chromosome and the resistance phenotype. And realizing that this is not just scientifically cool, but actually practically useful. We can actually use that as a process means to vaccinate bacteria against viruses by exposing them to a virus that's a problem in the industry, and then screening for CRISPR evolution, and then picking one that's made by nature that becomes resistant. And you do that a few times, and now you have a super immune, super dairy strain that's going to last forever and make the best yogurt and the best cheese forever. So the ability to recognize the scientific phenomenon of CRISPR immunization, but turn that into a patentable invention and a useful process that can be used in the industry and productized to make great cheese and great yogurt, that's the exciting part of the journey. It's not just the science. It starts with the science, but then on top of that, you have to have a practical idea that you can reduce to practice and then productize, and then hopefully eventually monetize. That's the process of creating value for everyone. And the scientist wins, the technologist wins, the industry wins, the consumer wins. And that's why we now have great yogurt and great cheese that's more sustainable throughout planet Earth. The ability of CRISPR not just to be an immune system in dairy bacteria, but also to be a molecular scalpel that allows us to rewrite DNA code is fundamentally revolutionary. If you want to change or rewrite the DNA code in any organism of interest on planet Earth. Of course, a lot of people work on human genetic disease, and we can use CRISPR to correct faulty, erroneous, mistaken human DNA. Gene therapies, cell therapies, and genetic disease, fantastic. But we can actually use that technology outside of humans to change DNA in other organisms of interest to humankind. So think like crops. We can go into plants that we grow as crops. You can do that in corn, you can do that in soy, you can do that in nuts, you can do that in vegetables, you can do that in fruits, including fruits you put on crepes, by the way. And then change the DNA code of those plants to make them more sustainable, to make them more pest resistant or drought resistant or heat resistant or frost resistant, or you can change their DNA content to change their properties and make them more tasty. All right, as always in French, everything starts with beurre, or in English, butter. You cannot cook French food without butter, as we all know. And it takes about a minute for the chemistry of heat to work through, and of course we can't have anything good without fermented milk. In this case, CRISPR enhanced cheese with amazing starter cultures, and then you can have French food without some meats. Put some French ham on there, of course, and a little bit of salt, a little bit of pepper. Perfect crepe. At NC State, we have a fantastic forestry program. And forest breeding is like a very important, locally trees matter substantially. It's a large bioeconomy. So tree breeding and tree genetics is of high interest to some of my colleagues at NC State. And sometimes as scientists, even as a food scientist, I just don't want to work with food scientists. We have people down the road who are interested in tree genetics. So why not use CRISPR in trees and expand the play field and expand or explore where we're going next and what we could do next with CRISPR. Not CRISPR in bacteria, not CRISPR in humans, not CRISPR in crops, but how about CRISPR in the biggest organism on planet Earth, trees?
Yeah, I knew we had a lot of problems in forestry concerning sustainability, concerning environmental resilience. And I truly believe at the time that CRISPR was a solution, but I had really no insights into how to turn that idea, that perspective, into something that could be real, something that could have a real world impact. So I wanted to meet Rodolphe. Tree improvement has many challenges, one of which is the long generation time of trees. Trees take anywhere from 10 to 50 years to reach maturity, and so as you can imagine, breeding trees can take a very long time in fact, and that's where CRISPR comes in. CRISPR provides the speed, the precision, the accuracy, and ways to improve and modify tree genomes in a way that no other technologies can do. In fact, we can now edit the genome of trees in as little as 4 months, compared to anywhere from 10 to 50 years in tree breeding. That is the power of CRISPR.
We're using CRISPR to go into the genome sequence of forest trees that are commercially relevant. And then we change their DNA content to make them more sustainable, to make them more resilient, to make them more resistant to pests and weather patterns, to make them more amenable to the industrial process. One of the major outcomes of forestry as an industry is the pulp and paper industry. They're the papers that we use at home, toilet paper, tissues, feminine hygiene products, diapers, or corrugated cardboard boxes that we get delivered, all derived from trees, all made out of wood. But unfortunately, it takes 2 metric tons of wood to make 1 metric ton of paper. And now we can use genetics to go into the genome of trees to make it more amenable to pulping and processing and use maybe 20% less wood to make the same amount of product.
At NC State University, we've created some of the most advanced CRISPR genome-edited trees in the world. And what we're going to see is a genome-edited tree next to a wild-type non-edited trees. We are going to peel off the bark of those trees to reveal the developing xylem, the woody tissue inside of those trees. In the wild type, when we peel off the bark, we'll see a yellowy blue wood, just as if you would see from any tree you find in the forest when you peel off the bark. But on the genome-edited trees, when you peel off the bark, you see a remarkably red wood. That is the result of CRISPR genome editing. When we knock out specific genes, we can change the coloration of the wood in ways that reflect the changes in the chemical composition of the wood that make it more sustainable, more efficient for bioenergy and pulp and paper production. A few chances in a scientist's career to really pursue something that is meaningful, something that's greater than oneself, and this is absolutely the case here. Rodolphe and I, we're doing this because we believe this is the right thing to do. This is going to change the world. It's going to make the world a better place. We're not doing this for ourselves. We're doing this for future generations to come, because the trees that we create using CRISPR are trees that are going to affect our children, our grandchildren, our great-grandchildren, and many generations to come.
In the next couple of years, by the time we reach 2030, CRISPR will have been deployed to breed crops and plants and commercialized in over 100 million farms to feed over 1 billion people. And the ability to create novelty, the ability to invent new things and have new ideas and have new inventions, I'm convinced is predicated upon the ability to navigate the unknown and discover new things and blaze new trails and find new paths and even go to places nobody's ever been before. To have that, you have to have an adventurous, curious spirit in the first place. And that's the exciting part of the innovation journey. And all we have left to do is just try it out and enjoy it. French crepe, simple, ham and cheese. There's no other way to have it. C'est bon.